Okay, so I guess we can begin. So welcome to the second pre-lunch session. Our next speaker is Anshuman Maharana from HRI, and he will speak about some studies in string phenomenology, and it's a 30-minute talk.
Okay.
So begin.
Thank you, Sherman. I'll first share my screen. Okay, so should I start?
Yeah, please begin.
So I'd like to begin by thanking the organizers and the team at IIT Roorkee for putting this conference up. And I'll describe work which is done in collaboration with 𝗰𝗵𝗶𝗿, 𝗦𝗵𝗶𝗶𝗍𝗍, Matteo Lecheri, Ratul Mahanta, Francesco Muia, Kajol Singh, and Kuber Sinha. So as the title indicates, this talk is going to be based on various recent work in string phenomenology. And string phenomenology has two aspects: the study of string compactifications, and the second, exploration of their phenomenology. And I'll touch upon both. So on string compactifications, we will look at certain systematics of explicit construction of flux vacua. There, we will find some novel solutions with n equals to 2 supersymmetry. We will also look at some flux vacua which are particularly suited for obtaining de Sitter minima. On the phenomenological side, I will look at the evolution of cosmological inhomogeneities. We know by now that there's a lot of interesting structure in the inhomogeneities in the universe. And I will present a scenario where these inhomogeneities can grow very fast, and they'll have some implications. Okay. Now, since I'm talking to a broad audience, let me start with some motivation for flux compactifications. The simplest string compactifications are the ones in which the stress tensors for the matter fields vanish. And these are the Calabi-Yau compactifications. But they have a drawback. They contain massless 4D fields, massless 4D fields in their spectrum, which are called moduli. And they mediate long-range forces of gravitational strength, which are in direct contradiction with the observations. So we need to look at more general compactifications, and this is where flux compactifications come in. And flux compactifications are compactifications in which the antisymmetric form fields that are there in the 10D supergravity actions, they have a non-trivial vacuum expectation values. And once one looks at these flux compactifications, many of the moduli fields become massive, and this is what makes them attractive to when one tries to connect to particle physics and cosmology. And more generally, detailed studies of flux compactification is a natural direction if we want to enlarge our understanding of the backgrounds that we can do string theory in. Okay, so my discussion will be set in type 2b. So let me gather some essentials for that. Here, the internal manifold is conformal to an orientifolded Calabi-Yau that I will denote by X. And the light degrees of freedom are the complex structure and Kähler moduli associated with the Calabi-Yau. Now, the effect of turning on fluxes in the 4D effective action, it is captured by a superpotential. It's known as the flux superpotential, and it is the integral of G3 wedge omega over X, where F and H are the three form fields of type 2b. Tau is the complexified dilaton, and omega is the holomorphic three form of the Calabi. And the forms, they thread the 3 cycles, and this leads to a potential for the complex structure and dilaton. Importantly for the fluxes, they satisfy Dirac quantization conditions, and hence their integrals over the 3 cycles are quantized. And they also have to satisfy a tadpole condition. That is, the integral of f wedge h over x, that is bounded by something that's called 2 times q d3, and that's the net negative d3 charge in the internal manifold. So that arises from O3 planes or racked D7 planes. Now, the above 2 implies that when we're looking for flux compactifications with specific properties, we have to solve Diophantine equations. So these are equations in integers, we have to solve these. Now, there are various aspects of this superpotential that are interesting. I will focus on flat directions or approximately flat directions in the flux superpotential, and that's based on these 2 papers. So why approximately flat directions or flat directions? Well, by now it's known that this is a generic feature when the number of moduli is large, as was pointed out by these 4 authors and later on by in various follow-ups. And they're also interesting from the point of phenomenology. You need an approximately flat direction for inflation. And as we will see, they also can be very useful in constructing de Sitter vacuum. And also they lead us to interesting solutions of type 2b supergravity in their own right. So let me begin by describing this work, which will appear soon. So what we do there is we analyze the types of condition between W and derivatives that can lead to a residual moduli space. Because if you have an approximate flat direction or a flat direction, you need a residual moduli. You are having a residual moduli space, and that implies some conditions between W and its derivatives. And imposing these conditions actually leads to simplifications in the Diophantine equations. And this allows us to find explicit solutions for the flux quantum numbers and the residual moduli space. So we have a good understanding of this vacuum. So instead of going through the general analysis that we do in the paper, I will go by examples. The first is about some novel solutions with n equals to 2 supersymmetry that we find. So the simplest relationship that one can think between the superpotential and its derivatives is a linear relationship. And that leads us to 𝗬𝗏-Minkowski flux compactifications with n equals to 2 supersymmetry on toroidal backgrounds. And interestingly, one can also make the choice of fluxes such that the dilaton is unfixed. So you actually have a flat direction along the dilaton. So this combination is novel, having n equals to 2 supersymmetry and a flat direction. And so we hope that this extended supersymmetry and the possibility to tune the dilaton makes these solutions ideal starting point for improving our understanding of flux compactifications. And this should be interesting from other points of view. I mean, a question that many people are interested in is what are the kinds of n equal to 2 compactifications that we can get from string theory? And it's easier to understand n equals to 2 compactifications. So we've got these n equals to 2 compactifications that we plan to study in detail. They should also be relevant for this classical Rajesh growth conjecture. Now let me move to the next topic, and that's related to the expectation value of the flux superpotential, which is called W0. Okay. And W0 much less than 1, its magnitude being much less than 1, is an essential ingredient of the KKLT construction. It allows for control over the higher order corrections in the effective action. So the question, what choice of fluxes lead to W0 much less than 1 is interesting from the point of view of constructing de Sitter vacuum. Recently, these 4 authors have provided a method to carry out such explicit constructions. And this is based on the following observations, that one can get W0 much, much less than 1 if in the large complex structure limit of the Calabi-Yau, the polynomial part of the superpotential is homogeneous degree 2. So this is a bit technical, let me elaborate. It is known that when one goes to the large complex structure limit, the superpotential is a polynomial which is at most degree 3 and exponentially small corrections. So if this polynomial is homogeneous degree 2, then you get W0 much, much less than 0. But the same condition of a homogeneous degree 2 superpotential implies that there is a scaling symmetry of W, and that leads to approximately flat direction. Approximate in the sense that it is a flat up to these exponentially small corrections. But we see that here W0 much, much less than 1 and approximately flat directions are tied. So as before, the condition on the superpotential that it is homogeneous degree 2 here translates to a set of Diophantine equations. Now, if you want to go ahead and carry out Taylor modularized stabilization, examine the phenomenological properties of these vacuos, it is important to understand the full set of solutions to these equations and their properties, as in, do they have any specific properties? So this is what was carried out in this paper in August. And here I will focus on the 2 modulus example, since here the analysis is the simplest. Okay, so in the 2 modulus example, one gets Diophantine equations in 4 variables. They're conveniently paired into M and K to 2 vectors. Now, I could write the Diophantine equations, but I think in the view of time, I'll not even write them explicitly. I'll describe the main features of how things go. So in solving these equations, the main challenge is that the flux inner product, which is F wedge H, is not positive definite. Okay? And this implies that when one writes down the tadpole condition, it does not cut out a compact region in the flux vector space. And that implies that in principle, there are solutions for arbitrarily large values of M and K, and this makes finding solutions quite difficult. But what one can show is that on the solution space, so after you impose the condition that you are on the solution space, this inner product is positive definite in that subspace. And also the ratio of 2 flux quantas minus K1 over K2, recall K1 and K2 were 2 flux quantas, that lies in Farey fractions at 2 times QD3. So recall that Farey n is the set of reduced fractions less than 1 whose denominator is less than n. So with these 2 conditions, one can effectively look for solutions. It can be helpful to do the last part numerically, which is scanning over the Farey fractions, but one can enumerate all the solutions. So for example, if you look, I'll just look at one example, which is the Calabi-Yau that is obtained from a degree 18 polynomial in CP1169. And this has an orientifolding with QD3 134. And we find that there are essentially only 2 solutions where W0 is less than even 0.1, and I list them. So the point here is, I think that what to show is that you can be very explicit in finding flux vacua and the values that the superpotential takes on. A few comments is that on the other hand, there are statistical expectations for how many vacua there are. And for this 𝗀, if one compares with the statistical expectation at low W0, as computed by Denef and Douglas, that's of the order of 10 to the power of 6. And this holds in general that these vacua seem to be very low in comparison to the number predicted by Denef and Douglas. So the natural question is, where are they remaining? Are there other families that we should try and find? And when can we trust the statistical approximations? So this is all work in progress. Now, before moving on to the cosmological side of things, I'd like to mention one more topic in type 2b, which is the subject of this paper. So type 2b flux compactifications is the place where we understand moduli stabilization and supersymmetry breaking best. So an important question is, how is the scale of supersymmetry breaking distributed in these? So is high scale supersymmetry favored or low scale or something like that? This question has been studied in the past, but we revisited the question. And what we were careful about is that we did the statistics only over points which correspond to the minima of the modularized potential. So we were actually looking at vacua, so that involved taking this fact into account, that you only do the sampling over the points which correspond to minima. And after that, we found that the results depend on the way moduli are stabilized. For KKLT vacua, we found a power law distribution for the scale of supersymmetry vacuum, So n vacuum is the number of vacua in this unit change in the gravitino mass, okay, dn vacua divided by n3 by 2. On the other hand, for the large volume scenario, we found a log distribution. Now, this is contrary to previous results, which put the scale of distribution of supersymmetry to be always power law with a preference for a high scale. So the log distribution is, of course, favors a lower scale, and phenomenological implications of this have been studied in detail by these 4 authors. Okay, so now I'll come to the final topic, which is fast growth of cosmological inhomogeneities, and this will appear this week with Subinoy Das and Francesco Muia. So understanding the inhomogeneities in the observed universe, such as those in the, say, temperature fluctuations in the CMB, is one of the challenges of modern cosmology. And there are 2 aspects to this problem. The first is the generation of the primordial fluctuations, that how did the fluctuations come about in the first place? And so this, something like inflation can give you. And the second, equally important, is the evolution of these perturbations through the history of the universe. And the work I will describe is about the latter. So let me quickly recap some basics about the evolution of cosmological perturbations. The key players are, of course, the tendency of gravity to collapse, pressure and expansion of the universe. They counteract this. Now, in flat space, there's the Jeans instability, which says that for long enough wavelengths, an overdense region is going to collapse in exponentially fast time in the linear theory. But things are a lot slower in an expanding universe. For instance, in a matter-dominated epoch for sub-horizon modes, the growth is proportional to the scale factor, which is power law in time. In a radiation-dominated epoch where there is pressure, it's even slower. It goes as log of the scale factor. In the standard lambda CDM model, inhomogeneities grow and structures form in the matter-dominated epoch. But as we probe the inhomogeneities in the universe at various length scales and greater accuracy. Growth of perturbations, and particularly if we have scenarios of fast growth, they can be very interesting. Now, let me come to our results. So I'll first describe the setting, the main ingredients, and the results. So our setting is an early matter-dominated epoch in the universe. So this is before Big Bang nucleosynthesis. There is the matter-dominated epoch. And this is a generic feature in string cosmology. And then a scalar-mediated force between the constituents in those epochs. So you have a scalar field that's mediating the force, and that again occurs commonly. The coupling is via the stress of the trace tensor. So given these two, we find that inhomogeneities can go very fast. That is, delta t grows with an exponent of the scale factor that can be much, much greater than 1. So let me come to the system of equations. There are 3 components in the universe that will play a role. One, so there are 2 cosmological fluids, which will be described by B and psi, and we will be using their stress tensors to describe them. And there's a scalar field. So these are the 3 components. And the stress tensors of the individual fluids are not conserved. There are violation terms. These violation terms are proportional to the traces, their traces, and the gradient of the scalar. And this system has been well studied in the past. It starts from work by Damour, Gibbons, and Goodlack. Amendola has explored various aspects of this system. And 2 is just for the purposes of illustration. You could have multiple components here. So because of this violation terms, the various components will in general exchange energy. Betas are the couplings. An order 1 beta is a Planck surplus coupling, but you can get larger values of beta in supergravity. So now let's come to our solution. Firstly, we find a new homogeneous background of this system of equation. So let me first describe features of this background. It has the following properties. Firstly, in asymptotic time, the energy exchange between the components stops. Okay, and the energy density of all the components, they fall off as matter. So everything is diluting as 1 over a cube. And that's good because that's where one can expect fast growth. And the scalar field is just oscillating about its minimum, the Hubble having fallen below its mass. And this, we end up in the solution for a large class of initial conditions, although we haven't charted this out fully, but this seems to be quite generic. It's like a tracker solution. So just I'll show a slide with the evolution. You have omegas, which are the fractional energy densities, and they are evolving. N is the number of e-foldings of the universe, and you see that within 2 e-foldings, everything settles in. The fractional energy densities don't change. Okay, now let me come to the perturbations. Having described the background, let's study perturbations in them. And for simplicity here, I will just set one of the couplings to 0. And we'll focus on modes that enter the horizon well before the scalar begins to oscillate. So this is a coupled system. You are looking at perturbations of there's Einstein gravity. There are the various components. But for the psi field, the equation is well described by this equation. And let's look at that. So this is the equation that describes the perturbations of psi, delta psi being the fractional overdensity. Primes here are derivatives with respect to the log of the scale factor. And so that's the number of E foldings. Omega psi is the asymptotic value of the fraction of energy density in the psi fluid. And you see that suppose I set omega psi equals to 1 and beta equals to 0. So that's the standard matter dominated epoch. There is the solution delta going as e to the power of n, which is just the scale factor. So we recover the usual story of linear growth for beta equals to 0. But with non-zero growth, one can get much higher exponents. And the growth is essentially controlled by the square root of omega psi times beta squared. Omega psi, of course, depends on beta. And but for instance, if I set beta like equal to 15, one gets a growth factor of 5.5 growth exponent. And this is very fast in the sense that if you start with primordial fluctuations, which are of the order of 10 to the power of -5, the kind that people talk about in the context of a scale invariant perturbation coming from inflation, then within 1 or 2 E foldings, the perturbations go nonlinear. Now, this matter-dominated era must end before BBN so as to accommodate the successes of nucleosynthesis. But a fast growth in this pre-BBN era can have many interesting implications, and we've just started to explore these. The first is compact objects. We can expect to form compact objects or primordial black holes. And our parameter range allows for primordial black holes in the lunar mass range, which is very interesting from the point of view of dark matter. The second is gravitational waves. When you have fast growth of perturbations in the universe, you produce gravitational waves. And these are in the high frequency range. So high frequency gravitational waves are expected to be a new probe of early universe. So in principle, one can have signals for these probes. So other than that, there should be many interesting implications for things happening at the shorter length scales. So that brings me to my conclusions. I talked about two things. The first is string compactifications, where I described novel solutions with n equals to 2 supersymmetry. I looked at how one could get solutions with W0 much less than 1. We also have some systematic methods to look at these, and there is some interesting structures in the Diophantine equations that we are getting. We hope to pursue this further. We have been using very elementary methods till now. On the phenomenological side, I looked at supersymmetry breaking. There we found a new distribution, a log distribution. And finally, I looked at cosmologies, where one can have a very fast growth of perturbation, cosmological perturbations, which should have some interesting implications. And to summarize, I'll say that there's many things to explore on both the sides. So thank you.
Okay, thank you very much for the excellent talk. So we have some questions. So first, we can let Alok Mishra ask his question.
Okay, hi Anshuman. I just had a couple of, sorry, yeah. So first off, Shiroman, do I have the permission to ask 2 questions, or I ask one, I wait my turn again?
You can, whatever.
Okay,
you wish.
I'll be real quick. So I've got 2 quick questions. So just correct me if I'm wrong. Since you guys have not, at least in what you talked about today, you have not explicitly included high derivative corrections. So let's say the alpha prime cube corrections. So you are within the regime of no scale supergravity, right? Is that right?
Yes, for the first part, I had not. When I was looking at those, when I was just focusing on the complex structure and dilaton.
Yeah. So actually, that brings me to my first question, which is the following. So we know that there's this, I think, which is something which you probably alluded to, or I'm not sure, this beautiful conjecture by Douglas and Ashok about essentially looking at the no-scale vacua. So you mean looking at the total number of no-scale flux vacua.
Yeah.
And there we know that it's basically given in terms of an integral over the moduli space. So back when this thing came out, one of my, in fact, back then, an undergraduate first-year student, as a summer project, we actually explored what are these two-parameter 𝗬𝗂 of the projective variety that was actually 11226. And so this, I think you made some statements about not really getting a power law in terms of the number of vacua. What we found was the following, that if one was working near or away from the conical loci, let's say probably there was just one of the projective variety of the 𝗬𝗂 that we looked at. So if one was away, one was actually getting a power law. And the logarithmic, I think you talked about some logarithmic dependence. So that is something which was actually when you were working near the conical locus. And in fact, that was interpreted as an attractor solution. So, I mean, that's sort of a remark/question to you.
Yeah, so I think that the distributions that I was looking at was the scale of supersymmetry breaking. So this is, I think this is the distinction that we made, that we computed the distributions after doing the moduli stabilization. So this, I mean, so for this part of the talk, we were actually incorporating the Kähler moduli stabilization. And so it could, so that's the reason for the difference with the old result of a power law distribution for the scale of supersymmetry making. What could be true is that the log distribution that you found could actually map to the logs that we have found after moduli stabilization, as in that part of the moduli space might be dominating for the LVA solution. That's what we have not looked at. But I mean, the reason why I think people found power laws for the scale of supersymmetry breaking is that they had not incorporated moduli stabilization. In fact, the reason why our results for KKLT and LVS are different is that we are incorporating the Kähler moduli stabilization in this part, in that later part of the talk.
Oh, so that means I probably misunderstood. I mean, I thought at some point you were talking about just the number of flux vacua not being a power law.
No, this is after incorporating the scale. This is after including supersymmetry breaking. So this is once you have stabilized the moduli, you ask that how does the number of vacua change as I change M3/2. And in one case, that goes as 1 over M3/2, and in the other case, that is proportional to M3/2. So it's a slightly different question.
I see.
But I mean, the logs and the power laws do show up, and it could be related to your initial understanding of the distributions that you're talking about. But this is, these distributions are about the scale of supersymmetry breaking. So this is dn vac divided by dm3/2. So how they change the number of vacua in an interval of m3/2.
Yeah, I mean, I just feel that intuitively, probably you would need to actually explore two regions, the complex structure moduli space, one near, one away from the conical singularities.
Yeah.
Especially if you're looking at the projective varieties, maybe. Okay. So
yeah. I think maybe that's related, but the way we kind of do this computation is that we boil the problem down to just looking at the distributions of W0 and G string. So that in principle takes into account the distributions that you are talking about.
Okay, and a thorny question, but I hate to put you on the spot, but still, I mean, so how does, how does this I mean, I haven't followed the story for a while, but how does the small W0 vacua address the swampland conjectures?
Well, see, I can tell you my view of this whole story in the sense that there are various things that need to be done very explicitly for us to be more and more confident about the existence of a de Sitter vacuum in string theory. And one of the things that I mentioned that the KKLT construction requires is a very small value of W0. Now, that is not easy to achieve because you essentially have to, you're dealing all the flux quanta are integers. Now, by tuning these integers, you want a small number. With statistical expectations, as I pointed out, the statistical expectations were that they're there. Now, you might like to go a step further where you actually find them, okay? And these recent developments show that you can find small W0 where you specify the Calabi-Yau, you specify all the flux quanta, and you compute W0 and you get a small number. So that's making one part of the set of things that we need to do in a more solid footing. The other thing about small W0 is that small W0 is very essential to control the higher order corrections in the effective action. So even if you believe, say, the swampland conjectures and you want to construct string vacua in the region where you trust them, having explicit constructions of small W0 is equally useful. I mean, the same challenges of moduli stabilization and understanding the system also come up if you want to construct a model of quintessence. So overall, this adds to the kind of things that we need to be very explicit about. And this is one aspect which I think has been cleaned up. There are more questions, but this helps.
I think 𝗬𝗫 would be very, very annoyed with any success that would be.
No, well, I think that, look, I mean, it's not that there are other questions left. So I mean, there's no reason to be, I think there's no reason to be annoyed by a table where they're just numbers. I think he won't, I mean, you know, there are things that we just have to clean up. And see, the other thing is that once you do these things, apart from knowing whether you can have de Sitter vacua or you're realizing quintessence, you will learn things about the phenomenology. As in, when you want to, say, compute the distribution of various quantities, what are the properties of various vacua, you need these kind of computations. So, yes, these are all useful, and as I said earlier, I mean, they will also be useful in getting information about string compactifications in general. It is enlarging our understanding of string theory in some sense.
Okay, so I think ICTS had a question. So.
Hello, Anshuman, this is Loganagam here.
Yes.
Yeah, so I just wanted to ask you a question about this cosmological scenario that you presented at the end. This fast growth of cosmological inhomogeneity, like, why doesn't this, wouldn't it completely destroy the fact that the CMB anisotropies are suppressed and so on? Like, why wouldn't this contribute to?
Yes, so the thing is that these are modes that enter the horizon well before the CMB scales. So this is at a short scale. So this will not affect things that are happening at the CMB scales. So this is a completely different length scale. So if you believe in something like inflation, what would happen is that you start off with everything which is scale invariant, as in you have delta equals of the order of 10 to the power minus 5 for all scales early on. And then you evolve. So some scales will grow faster than the others. So this is a computation of what's called the transfer function in cosmology. So that's it.
Okay, just one more question. So you were talking about these gravitational waves and so on at some in your talk. So you have some estimate of like what kind of, let's say, B mode polarizations will show up and so on. Is that how?
Yeah. So this is not within the context of the CMB. This is just a stochastic pure gravitational wave. So you should think of it as trying to detect the gravitational wave directly. So this is in the higher frequency range. We go around 10 to the power of 2 hertz with LIGO. So this can be we've just done the ballpark estimates. This is probably 4 or 5 orders of magnitude more. So here there are no experiments, but there is an active community which wants to have experiments in this. So they want to join the gravitational wave collaboration team. But this, because the earlier you have the phenomena, typically you get higher and higher frequencies. So this can be a new probe for early universe.
So sorry, just to make sure that I understand. So you're saying this only affects the larger part of the spectrum, and it does not have any effect on this R and so on, the tensor to scalar ratio.
Yeah, it will not. It's a different. It's in a different range. Its origin is different from inflation. Okay, and this will be just like a stochastic gravitational wave, which will not have any direct effect on the CMB scales.
Okay, thank you.
Okay, so let's thank Anshuman for a very nice talk. And okay, we're going to move on to the